Yes, hey guys, welcome back. And now let's solve Bellman-Ford or shortest distance from source. But yeah, if we talk about Dijkstra and we don't talk about Bellman-Ford, then yeah, it is not very good. Mainly because Dijkstra is for undirected graphs while Bellman-Ford is for directed graphs. And yeah, what it is like? Yeah, let me give an analogy. Like it is like drinking orange juice after brushing. Like yeah, you shouldn't. It's not like you shouldn't drink, but if you drink, then you will be left with a sour taste in your mouth, and you will be wondering, okay, why is this happening to me? Where I went wrong in life? And yeah, why? So why is Bellman-Ford required after learning Dijkstra? It's pretty simple. Mainly because Dijkstra works on undirected graphs, and Bellman-Ford works on directed graphs. And yes, so let's directly go on with how Bellman-Ford works. So Bellman-Ford is mostly similar to Dijkstra with some small modifications. Like for in Dijkstra, what we do is we use a heap, and then we store the source node, pop the source node, go through its neighbors, and update the distances array. But we can't do that in Bellman-Ford mainly because it's not guaranteed that we'll be able to reach every node in the vertex, every node in the graph. And when you can't reach any node, yeah, obviously the distance will be infinity. And since those distances can't be reached, those have to be updated properly. And mainly for that reason, we use Bellman-Ford for directed graphs. And one more thing with Bellman-Ford is that it works on negative edges also. But when you're using Dijkstra and if you get a negative edge, then yeah, obviously your solution will fail. So what we have to do is again, it is completely similar to Dijkstra. We have to have a default dictionary to maintain the graph. But the difference between Dijkstra and Bellman-Ford is that while in Dijkstra what we did is we pushed into a heap. In Bellman-Ford what we have to do is we have to continuously iterate through our graph v minus 1 times, where v is the number of vertices given. This is mainly to update all the edges again and again, so that after first iteration you might have found a smaller path between two nodes, and after second iteration you might want to update that smaller path to our previous nodes. For example, that path might be connected to our previous nodes and you have to update it also, and that is obviously not possible in only one iteration, so we have to iterate v minus 1 times. After that, this is called relaxation, and after this again we have to check for negative edges. What does negative edge mean? Yeah, imagine the same thing 0 to 1, but if it was minus 9, then obviously you can't go from 0 to 1 in a negative way. Yeah, 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 you understood. I hope you understood why we can't go in negative direction. Mainly because the direction going outgoing is positive, and so the weight also might be positive, and it can't be negative. So yeah, to check for those conditions, to make sure that that does not happen, we have to go through the our final distances array, of our final graph one more time and check for negative distances. And if you find a negative distance, then according to our problem statement you have to return an array consisting of only ones. So yes, like it's better to directly jump into it. From what you have to do first is to import all the necessary items. So yeah, from collections we have imported default dictionary. For why do you need default dictionary? To make the graph. So first let's declare the graph. Yeah, and I hope you know why this is being done like this, how graph is being created and all. Let's return something and check it out once, how the edges are given. Okay, yeah, this is a very small input, and obviously that is not enough information for us to do. And read the input format once and check out how we have to put it. It is given that we have two spaced integers, the vertex and the edges, denoting a corresponding number of nodes and edges. So let's go with this one. So just look at the example once. You have 3 vertices and 4 edges. So you have to have 3 vertices, 4 edges, and declare them in the form of from node to node and weight. From node to node and weight. And then you have to give the start node. The start node over here is 2. So let's run it once. Yeah. So the input format which you are given is start node to the from node to node and wait, from node to node wait. I just check it out once. So 0 to 1 the distance is 5, 1 to 0 the distance is 3, 1 to 2 the distance is -1, and 2 to 0 the distance is 1. And so yeah, let's go over it. Now first let's define our graph. So I hope you know how to do that. So you have to iterate for every edge in edges. So look at the input format again once. So it is from node, and I am just unpacking the value of each array, and then yeah, append takes in only one input, so you can't you have to put a give the input format in the form of a tuple. Yeah, just print graph once to see if you have done it properly. Let's look at this. From index 0 there is only one outgoing edge to 1 with weight 5. From 1 there is one outgoing edge to 0 with weight 3 and other to 2 with weight -1. And from 2 there is one outgoing edge to 0 with weight 1. So now what we have to do? Again the same thing, declare a distances array, and yeah, it is telling that if the vertex can't be reached from S, then mark it as 10 to the power of 8. So let's declare distances array. Yeah, I think we can directly do 10 to the power of 8, mainly because if we can't reach the vertex at all, then the answer should be written in the form of 10 to the power of 8, and rather than declaring infinity and then changing it back to 10 to the power of 8, we can do this, I think. And then again the distance from the source, if you're standing on the source, then the distance is 0, so distance at source is 0. Yes, so yeah, again if you remember for Dijkstra, what we did is we pushed the source node to the top of our heap and then popped items from the popped from the heap, added its neighbors and updated the distances. But here what we have to do is we have to go through each node v-1 times. We have to iterate v-1 times through each node, and then again check the distances in each node. So yeah, we are iterating each v-1 times through each node. Rather than calling it let me call it node. And then yes, since now you have the node, you have to check for neighbors for neighbor, and this is again unpacking the value directly rather than unpacking it later. It is node, not neighbor. Now again you have to calculate the tentative distance, and if you remember in Dijkstra's, what we did was we took the current distance from the current node and multiplied it with the weight to the neighboring node. So do the same over here. Is what you'll do, it is distance from the current node and add the weight to it, add the weight to the neighboring node. And now again you check if our current distance is less than the tentative distance, the tentative distance is less than the actual distance at the position neighbor. It's not distance at the position node, because you should not check the distance from the node to the node itself. You have to check to which neighbor the distance you have calculated corresponds to. And yes, if it is less than, then you obviously update the distance. You update the distance to the tentative distance. And yeah, this should actually, the distances array should already have all our values. So let's print it once. Again I have called it distance, keep the naming consistent. Yeah, okay, yeah, you directly have the input, you have the output matching to the actual output, but yeah, it is given that if there is a negative cycle, then you have to return -1. For example, yeah, you consider this distance was -100, then you would obviously never be able to reach 2, mainly because whatever you did, the distance would become negative. So you have to check for that again in the same way. But rather than iterating v minus 1 times for, we can just go through each node once. So node in, yeah, and then go through neighbors of each node and get the weight. Where you will check it, it's in graph. And then yes, you check for the distance, and if you find the distance is, and yeah, again you have to calculate the tentative distance first. So let's calculate that. And yeah, if the tentative distance calculated becomes less than the actual distance found, now it means that there was some negative cycle over there. That's the reason the shorter distance already found is again becoming lower. And if that happens, then they're asking to return an array of -1s. So if the tentative distance becomes less than distance at the position neighbor, again it's distances, not distance at the position, then what you have to do, you have to return an array of -1s. Or else you can directly return distance. Let's compile it once. Again it is distances, not distance. Okay, now let's do the same, but make this node -100 to check if our value is returning properly. You have to get an array of all ones. Okay, yeah, read the statement properly. If the graph contains negative cycle, then return an array consisting of only -1. So it should just be -1. There is no need to return for all the elements, just return an array of single -1. Yeah, I think this is it. So let's submit it once and celebrate if what we're doing is working. Okay, okay, the code output is 9,000,000 some 93, but it should be this one. Why is that happening? Let's just go through the input once. Okay, the thing which you have to notice is there is no node from 2 to 3. That means that, okay, yeah, wait, let me just draw the node out. So according to the given input, you have 0. Okay man, I am no Leonardo da Vinci, so don't expect me to draw very good. You have 0, 1 with, okay, this is really hard, 2, and then you have 0 to 2 with weight 7, and then you have 1 to 2 with weight 4. But yeah, this is the main thing. 3 to 4 is actually disconnected. Yeah, 3 to 4 disconnected, so you will never be able to reach 3. But according to what we have done is, we have imagined that we might be able to reach 3, and we have updated the distance between 3 and 4. So that's why the distance of 3 is 10 to the power 8, but the distance between 3 and 4 has been reduced. Imagine we had another node like 5, and we had another node like 7, and if this was connected over here, then yeah, what we have done would work. But obviously this is not the case, and there is no connection between 5, 2 and 3. That's why the shorter distance between 3 and 4 was calculated. But since there is no connection, we are directly returning that distance, and we don't want that because our source node is 0 over here, and there is no actual distance between 3 and 0. So the value should be 10 to the power 8. Yeah, it would be better if geeks for geeks gave an example like that also, rather than just two very simple examples. So yeah, it's not difficult to circumvent that. So let's just make it float of infinity. Yeah, this makes sure that those kinds of updations don't happen. And since what you have to know, if you know concept of math, then you will know that obviously you, you can add any number to infinity and it will still stay infinity, and it will never become less than infinity or greater than infinity. There is no such thing as greater than infinity or less than infinity. So yeah, now you can just update all the values of our distances array and check if it is float of infinity, then you will return 10 to the power of 8. Yeah, if distances. Then what you will do? You will set it to be equal to 10 to the power of 8. Yeah, and now it should work. Let's just copy that submission once. Okay, where is that? Yeah, let's just copy it once and check it out. What have I done? Okay, something is not at order. What is the invalid syntax? FLOAT of infinity for an range length of distances. Ah, yes, yeah, I forgot to put if distance is at position. And yes, now whenever there is some node which can't be reached, as they have asked, we are returning 10 to the power of 8 rather than infinity. So now let's just submit it once. And yes, all the 69 test cases passed. Nice. And yeah, just be careful of what you're doing and be wary of where an error can occur. For example, according to the given statement, we have to return -1, but first I tried returning an array of negative ones, and that was obviously not the case. And read through all the constraints and the description properly. And again, check for edge cases, like what will happen if the graph is disconnected. Then you will obviously update the weight to those disconnected graphs, but you will not check that if there is a connection between the source and the disconnected graph, and you will obviously return something wrong, like what happened to me. And yeah, no one is perfect, and that will happen to everyone. So yeah, whenever things like that happen, don't bang your head on a wall and think where you went wrong in life. Just learn to push through and you will obviously find a solution. So yeah, thank you.